What if I told you there was an invisible network in the sky guiding one of the world's most elite explorers? Forget pheromone trails. Desert ants use celestial navigation to run perfectly straight back to their burrows. Discover how their compound eyes hack the physics of sunlight. To find the source of this biological GPS, we have to look at the Tunisian Sahara salt flats. This is a featureless 158-degree wasteland. It offers no rocks, no shrubs, and no visual landmarks to guide a traveler home. This is the hunting ground of Cataglyphis fortis. While other creatures retreat from the midday heat, this solitary ant scavenges for food. Because the ground is so hot, standard chemical pheromone trails, the navigation tool of most ant species, evaporate almost instantly. To survive an environment that destroys both physical landmarks and chemical trails, this ant has evolved a radically different way to find its way back to safety. The ant's journey begins with an exploration phase, traveling hundreds of meters in chaotic, looping zigzags. The moment it finds food, everything changes. It instantly rotates and runs in a mathematically straight line directly back to its origin point. The precision required here is staggering. The nest entrance is a hole the size of a needle puncture, completely invisible to the ant until it is only a few inches away. The ant isn't recognizing the landscape or retracing its steps. It is actively calculating a new return vector from scratch with every move it makes. This calculation is powered by Rayleigh scattering. As sunlight enters the atmosphere, it creates a predictable gradient of polarized light. This forms a geometric grid across the dome of the sky that is completely invisible to human eyes. The ant reads this grid using its dorsal rim area, a specialized cluster of UV-sensitive photoreceptors at the top of its eyes. These receptors contain microvilli arranged at perfect 90-degree angles to one another. These orthogonal sensors allow the ant to detect the oscillation plane of light. By comparing these angles, the ant can determine its exact heading even when the sun is hidden behind thick clouds. This atmospheric compass is hardwired into the ant's optical anatomy, providing it with constant absolute directional awareness. But direction is only half the puzzle. To know where it is, the ant uses path integration, a form of dead reckoning where it continuously updates its homing vector by integrating its heading with every single step taken. Despite traveling hundreds of meters through an alien landscape, the ant does not record a visual memory map of the terrain. It is essentially flying blind to the landmarks we would rely on. Instead, a tiny cluster of neurons fuses its compass heading with an internal pedometer. This creates a homeward vector based purely on geometry, entirely ignoring the physical appearance of the surrounding landscape. This entire real-time mathematical algorithm runs on a brain the size of a pinhead, showcasing incredible biological efficiency. To prove the ant used an internal pedometer to track distance, researcher Matthias Wittlinger conducted a famous experiment to manipulate the ant's stride. After ants found food, researchers glued tiny bristles to their legs to create stilts, while others had their legs shortened into stumps. This chart shows the result. The ants on stilts had a longer stride and overshot their nests, while the ants with shortened legs stopped too early. They were all walking the same number of steps, but their physical stride had changed. When researchers applied polarized filters over the ants' eyes to rotate the incoming light, the ants immediately turned in the wrong direction, confirming they prioritize light geometry over sight or scent. These results confirm that the ant operates as an autonomous mechanical step-counting machine. But what happens if the sky is so dark or overcast that the UV polarized light is completely blocked? The ant has a hidden backup. It possesses a secondary navigation system sensitive to the Earth's geomagnetic polarity, allowing it to maintain its homeward vector even when its primary optical compass fails. This biological system is layered with redundancies that rival the most sophisticated aerospace engineering. Our own navigation is fragile by comparison. We rely on a massive infrastructure of satellites that can be easily jammed or blocked by physical obstacles. To fix this, engineers have built AntBot. This autonomous rover abandons GPS entirely, relying instead on optical polarized light sensors and mechanical step counting to find its way. The ant's brain is a functional model for edge computing, a paradigm where data is processed locally at the source rather than on a distant server. By handling complex trigonometry within its own neural clusters, the ant achieves extreme energy efficiency that could soon power deep space rovers. The most advanced navigation technology on the planet evolved in these deadly salt flats, outperforming systems developed in Silicon Valley labs. The question is, does the future of artificial intelligence really need giant supercomputers? Or are we just not smart enough to mimic the efficiency of an ant yet? Share your theories below, hit subscribe if you like science visuals like this, and we'll see you in the control room next time.